Hello everybody, welcome back to the Gregorius Maths video. Today we're carrying on from yesterday, where we will traverse through the language of group cohomology. And as I make this video, I realize it's actually like I think it's quite a nice introduction to cohomology in my opinion. And it may motivate me, no promises, to make a slightly longer talk on the subject, with slides and stuff. But okay, anyway, in today's video, instead of focusing on hypothetical videos that I may or may not make, in today's video we're carrying on. And where are we carrying on from? Well, yesterday we saw that a 2 cocycle in our case was a function which takes in 2 ones and outputs a 10. So okay, we were looking at addition mod 100, and we noticed that the carrying function is important. So the carrying function is an example of a 2 cocycle in that it takes 2 ones and outputs a 10. So if it takes in 2 ones whose sum is less than 10, then it outputs 0. And if it takes in 2 ones whose sum is greater than or equal to 10, then it outputs 10. And importantly, the function z, the carry function z, satisfied these properties here. Our first one is the cocycle formula, and the second one is this normalization formula here. And these were motivated by the fact that we would like to use a cocycle to define a group structure. And so this one sort of associativity, and this one is like the identity. Yeah, the identity. I don't know why I'm lost for words, but okay, anyway, you get the idea. So that's sort of a brief recap. So this is sort of the general definition of a cocycle, is if it satisfies these properties here. And in today's video, we are going to look at extensions, group extensions, and we're going to take this all the way through and motivate and in the end define the second cohomology, and show that it's in bijection with the sort of equivalence classes of extensions. So that should be quite informative, I hope. Yeah, so let's strap in our seatbelts and get right into it. So the first thing we want to define is what is an extension. So definition: an extension of O by T is an abelian group E where T is a subgroup of E, such that E mod T, or yeah, E mod T is isomorphic to O. Okay, so why is this relevant to what we were doing in the last video, you may ask? And to answer that question, we should dive in a little bit into what do the elements of E actually look like. So first things first, obvious thing out the way, is that the tens are a subgroup of E. So what we'll do is for some 10, we'll write A0 to be an element of E, where A is just an element of T. And notably, we'll write 0, 0 as the identity. So 0, 0 is the identity in E. Okay, so these correspond to the tens, basically, because the tens are a subgroup of E. Now, how do we make sense of the ones? Well, consider the projection map from E into O, which is defined, which just sends the some A to its equivalence class via this isomorphism here. Then, for every single one B, so for all ones B, define 0B, so 0B to be X, where we've chosen X such that P of X equals b, like so. So we just pick some random x and we say 0b is now x, and the reason we pick x is because p of x is b. So note it, okay, I want to clarify here. We've picked one random element x. This is not for all x such that p of x is b, it's this. No. We just picked an element x and we're calling it 0b. So in general, we write the element ab to be a0 plus 0b, like so, which is sort of what you would expect. Now, okay, okay, here we go. So what I claim now is that every element of E can be written as AB, and uniquely at that. And the reason for this is, if we let Y just be an element of E, and we have, say, well, P of Y has to be something, so we'll just call P of Y B, then this means that Y minus 0B is in the kernel of the projection map, which I called pi, but for some reason I'm saying P, so I'll just change this to P. But the kernel of the projection map is precisely T. Therefore, there exists some A such that A0, because remember this is an element of T, is equal to Y minus 0B, and therefore we can write Y equals AB. So that shows that every element of E can be written in this form, and the reason why this is unique is, well, sort of a more crude argument, but nonetheless satisfactory. So notice this definition is very strict on the order of E. Indeed, it only gives you one possible order of E by Lagrange. It tells us that E must have order 100. And, well, there's only 10 options for the 10s, and there's only 10 options for the 1s. And so the elements of this form, there's only 100 of them. And if every single element of E can be written in this form, then it must be unique, because there's 100 elements of E. So from now on, we'll just understand elements of E as being in this form. And hopefully this sort of motivates somewhat how this can be similar to the, or how this relates to yesterday's video. So, okay, now what we need to talk about is the group operation on E, because, well, we have that A1 0 plus A2 0 is equal to A1 plus A2 0, like so, by the operation, because these are just elements of T. We also have, well, that 0b1 plus 0b2 is 0b1b2. Oh no, sorry, we don't have that. Sorry. That's completely false. And I'm talking nonsense. Let me not. That's the whole point, is that we don't have that. Okay, okay, let me proceed. So we have this. But, okay, now what about just A1 B1 plus A2 B2? Well, by the projection, if you apply the projection map to this, because the projection map is a homomorphism, what you'll see is that P of this thing has to be B1 plus B2. So, in other words, in the ones column, we must have B1 plus B2. But what we don't necessarily have is that it's in this column we have A1 plus A2, because otherwise we would literally just be saying E is the direct product of O and T, and we'd be done. So the whole point is that that's not necessarily true. So, definition, here's a definition. The cocycle associated with E is a map which takes in, we'll call Z, is a map Z which takes in two ones and outputs a 10, such that, and the way it's defined is 0b1 plus 0b2 is equal to Z of b1, b2, and then b1 plus b2, like so. So, this is very appropriate terminology. Why is this very appropriate terminology? Because by associativity, this map here satisfies this, and by the identity, by the fact that 0, 0 plus 0b2 will just give you 0b2, we also have this is true. So this map Z is a cocycle, so we've used good terminology here, and notice also that this fully determines the addition in E, because then we have A1 B2 plus A2 B2 is equal to, well, if you break it down as A1 0 plus A2 0 plus 0b1 plus 0b2, you just get A1 plus A2 plus Z of b1 b2, and then in the second column you get b1 plus b2. So, okay, so this fully determines our group structure in E, and so what we have is that an extension gives us a cocycle. So an extension gives us a cocycle, but also if you have a cocycle Z, then the collection of elements of the form A, B, where A is in the tens and B is in the ones, along with this cocycle where the addition is defined like this, well, that gives you an abelian group where, okay, the fact that it gives you a group follows immediately. Abelianness is non-trivial, but follows if you mess around with the cocycle condition and you are given the fact that the ones and the tens are both abelian as well. And if you mess around here, then you get an abelian group. So what I'm saying here is extension gives me a cocycle, but a cocycle also gives me an extension. So now the natural question is this correspondence one-to-one? Is it that these are in bijection? Yeah, is there a one-to-one correspondence? This cocycle matches with this extension, this cocycle, you know what I mean? Here's where cohomology comes in, because the answer to that is no. But we can amend our bijection to get cohomology, basically. But okay, first question maybe to ask is, what does it even mean for two extensions to be the same? Well, that's a great question. So, definition: two extensions E and E prime are isomorphic if what? So sorry, I should have, okay, if there's some map phi, let's call it, between E and E prime, such that the restriction map from T to T is the identity, and the induced quotient map phi phi bar, I'll call it, from O to itself is the identity. Okay, this is I think it's quite a natural definition. Okay, now here's a really important theorem, which will really motivate where the definition of sort of group cohomology comes from. So here we go. So, given E and E prime extensions with associated cocycles, which I'll just call ACs, Z, Z prime. If there exists a map H, which takes in a 1 and outputs a 10, such that H of 0 equals 0, such that Z of B1, B2 minus Z prime of B1, B2 is equal to H of B1 minus H of B1 plus B2 plus H of B2. Then E and E prime are isomorphic. Okay. So this is the theorem that I want to prove. So we're given this for all B1 and B2. Now, how do we show this? Well, how about we just try to construct our isomorphism? And a natural candidate that springs to mind is define phi of AB to be A plus H of B, B. Now, notice immediately, in the definition of the isomorphism, this is a homomorphism. This has to be a homomorphism. I don't know if I said that in words or not, but that has to be that's the key detail. Apologies. Anyway, so let's define this map. And the reason why this is such a good definition is because immediately, if you restrict this to just T, i.e. forms elements of the form A0, because H of 0 is equal to 0, you just get A0. So on T, this is the identity. Good. Now also, this is equal to A, B, plus H of B, 0, like so. And therefore, because this is just an element of T, AB and phi of AB are in the same kernel, in the same coset. And so if you look at the natural restriction map on the quotients, because this ends up in the same coset, it's also the identity map. So all we need to show is that phi is a homomorphism, and then we'll have shown that E and E prime are isomorphic as extensions. So let's dive into this. First things first, what is phi of A1, B1 plus A2, B2? Well, this is equal to phi of A1 plus A2 plus Z of B1, B2, B1 plus B2. And this is equal to, well, now we apply our definition, phi of A1 plus A2 plus Z of B1, B2 plus H of B1 plus B2. And then in this, we have B1 plus B2, like this. Sorry, I don't know why I put phi. This is just what it is, yeah, okay, sorry. Yeah, by definition of phi, you just get this. Now, on the other hand, we need that this is equal to phi of A1, B1 plus A2, B2. So let's do that. Phi of A1, B1 plus phi of A2, B2. This is equal to Well, what's this? This is just a plus h of b1, a1 plus h of b1, b1, plus a2 plus h of b2, b2, and this is equal to a1 plus a2 plus h of b1 plus h of b2. Again, I can mix and match because addition is abelian, so it's fine, commutative. Plus, and this time this addition is in E prime. So now we get Z prime of B1, B2. And in the second column as B2, we get B1 plus B2. So if we look at this, these two have to be the same. Oh, sorry, they don't have to be the same. But if we look at them, what do we have? Well, Z, if we rearrange this, we get Z of B1, B2 plus H of B1, B2 is equal to H of B1 plus H of B2 plus Z prime of B1, B2. So by the hypothesis here, this is a homomorphism, and so we're done. This is an isomorphism. And so I'll just put the box because I don't want to write all that. Okay, so this equation here somehow is really really important, really useful. So why don't we give it a whole definition? So definition, given a map H which takes in a 1 and outputs a t, such that H of 0 equals 0, define the coboundary. If you're familiar with homology or cohomology, then this is very suggestive naming, but if not, it's the coboundary. That's what it's called. Define the coboundary of H, delta H, to be a map which takes in two 1s and outputs a t, where delta H of B1, B2 is given by this formula here. Where is it? There it is. H of B1 minus H of B1 plus B2 plus H of B2, like so. So this is a definition of a coboundary map. Now, okay, here's where things get cool. So we have, if two cocycles differ by a coboundary, then E and E prime are isomorphic. What I want to show now is the other direction, that if E and E prime are isomorphic, their associated cocycles differ by a coboundary. So theorem, other way around. I'll just put the other arrow, implication arrow, because I don't want to write out the whole thing. It's okay. Proof. Okay, so how do we prove this? Well, okay, let's say we're given some isomorphism phi between E and E prime. Then, what do we want? Well, we need to define some coboundary such that the difference is a coboundary. And a natural one to consider is define H, which takes in a 1 and outputs a 10, by phi of 0b equals, well, this has to be, by the definition of an isomorphism, it has to be still something b. And, well, okay, in this slot, why not just put H of b? Let's try this. What does this give us? Well, use the fact that phi is a homomorphism. So phi of 0b1 plus 0b2. Well, this is equal to, on one hand, phi of z of b1, b2, b1 plus b2, which is equal to yeah, which is equal to phi of z of b1, b2, 0 plus 0 b1 plus b2. So we saw breaking it down now into the tens part and the ones part. And well, this is an isomorphism of extension, so it has to be the identity on T. So this is an element of T. So this is the identity, so it's just z of b1, b2, 0, plus, then phi of this is by definition h of b1 plus b2, b1 plus b2, like so. And then this is just equal to z of b1, b2 plus h of b1 plus b2, b1 plus b2, where now the fact that there's no z term in the tens is because there's a 0 here. So we use the normalization condition. So we can just add these together now. So that's on the one hand, we have this. But on the other hand, phi of 0 b1 plus phi of 0 b2 is equal to, well, this by definition is just h of b1, b1 plus h of b2, b2. This is equal to, by definition, now we're adding in e prime, so we get h of b1 plus h of b2 plus z prime of b1, b2. Yeah, and then b1 plus b2 in the last section. And well, because phi is an isomorphism by assumption, these two have to be equal. So in other words, we must have z of b1, b2 plus this is equal to this. So let's move this to that side, move that to that side. We get minus z prime of b1, b2 equals h of b1 plus h of b2 minus h of b1 plus b2. And so, therefore, this is equal to, and this is equal to delta h of b1, b2. And we're done. So, what do we have? Well, I said earlier, are cocycles and extensions in one-to-one correspondence with each other? And these two theorems here answer that question. The answer is no. However, two extensions are isomorphic if and only if their associated cocycles, the difference of their associated cocycles, is a co-boundary. So, we can view this in terms of quotient group terminology. I'll write the final part in here. So if we write Z2 of 0t to be the set of all two cocycles from O cross O into T, and we have B2 OT to be the set of all co-boundaries from O cross O into T, then, well, okay, first things first, notice that a co-boundary, this is itself a cocycle. Now, you can immediately see the normalization condition by the fact that h of 0 is 0. The cocycle formula, just plug it in and you'll get it, basically. It's a bit long, but you'll get it. So this itself is a cocycle. So what am I saying? I'm saying that a set of co-boundaries are also, another thing to note is that the set of two cocycles is itself an abelian group under addition. You just add the cocycles. And also the set of co-boundaries is an abelian group under addition, because you add two co-boundaries, you get this back a co-boundary. And so, what was I going to say? Yes. So these two are abelian groups, and the group of co-boundaries is a subgroup of the group of cocycles. So we define the second cohomology group of O with respect to t to be the quotient group of the cocycles mod the co-boundaries. And this is directly in bijection with the set of extensions of O by t. Because all that we're saying when we say that they are isomorphic if and only if they're cocycles, the difference is a co-boundary, all that's saying is the two extensions are isomorphic if and only if their associated cocycles are in the same coset. So what am I saying? That the second cohomology of O with respect to t precisely classifies these extensions. And so, yeah, hopefully that's it. I don't have anything more to say for now on group cohomology, although one can push this further. So, you know, stay tuned. There might be more on this to come. Not on the advent calendar, though, but later on. But hopefully that explicit example gives good intuition for why the second cohomology group corresponds to extensions. I think this is a really nice example. And yeah, I'm just happy to have put it on YouTube. So in any case, I'll see you tomorrow. And yeah, hopefully you enjoyed watching this as much as I enjoyed making it. So yes, I'll see you then.